Good morning. Dr. Stewart back with you today. We're going to do some mathematics this morning, and we're going to show you how to visualize functions. So as you have taken algebra and move into pre-calculus and then calculus and beyond, you become very used to looking at and dealing with functions of x and y. And so what we're going to do today is show you how you can quickly visualize what that function looks like when you look at it. All right, now, why would we want to do that? Well, one reason is when you're trying to understand, say, the behavior of a system, you will want to model it. And when you model it, you may use an equation using some of the laws of physics or dynamics or whatever, or electrical circuits, and you will want to capture that behavior in some type of mathematical form. And often that'll be some function of x giving a value of y. Okay? So what we're going to do is show you how you can visualize the picture of that function whenever you're faced with some complex mathematical expression. The brain is very good at reacting to pictures. Seems to be an acquired trait that most humans have, and probably had something to do with survival skills way back when. So we're going to give you the opportunity to convert mathematical expressions into pictures and do it very quickly. As you go into a college curriculum, this is very important because you're going to be faced with all kinds of mathematical expressions, and if you can visualize what's going on, you're a step ahead. Okay? So the visualization of functions is what we're talking about here. And let me just start with a function, which is a trig function, to give you an example of how you can use this. So let's suppose we have a function that is y is equal to 3 sine of 3x, okay, plus 2. So let's suppose you confronted that in, say, your modeling or in reading a book about some type of behavior of systems, and you looked at that and said, well, I really wonder what that thing looks like as it varies through the values of x. So let's see how we do that. Well, first of all, we need to break it apart. What is the class of function? This would be a trigonometric function, and it would be a function of the sine category. Remember, in trig we have sines, cosines, and tangents, and then the reciprocals of those, secant, cosecant, and cotangent. So this is the sine function. It has a 3 out here. It has a 3x in there, and it has a 2 tagged on to the back end of it. So let's see how we might visualize that. So first of all, the sine function looks something like this. It starts at 0, and again this would be y and this would be x, okay? And it starts here and goes like this, and the period from here to there is 2 pi. So this distance from here to here is 2 pi radians, which is basically one loop around the circle. So as we would go, if we had a unit circle here, and we drew a hypotenuse out this way and dropped a perpendicular down here, we'll just call this h, and we'll call this the opposite side and call this the adjacent side, okay? As you would rotate this around the circle, and let's call this the angle x, which is our independent variable, we would see that one trip around the circle would bring us right back to where we started, okay? And as we go around this circle, the sine function goes up, comes back down to the x-axis, then goes negative, and then comes back, and that would be one complete cycle. So the general class of this function is sine, and it looks like that. Now, we have two modifications here and here that are outside the sine function. Let's see what they would do. Well, if I look at this and say whatever this is, I'm going to add 2 to it. 2 just means we raise it up 2 units. Okay? And this, the 3, stands for the amplitude of that function. And whereas the normal sine function has a +1 to -1 range of that function, this would tell us that the function would go 3 high and 3 low. Okay? We're going to draw this in a second. What about this? The 3x. That tells us that whatever you put in there for x, you're going to multiply it by 3, which means that the function is going to behave 3 times faster than the normal function. Because whatever you put in for x, you're going to multiply it by 3. So if I put in 1, I'm going to have 3. 3 times 1. So it's going to behave much more quickly. In fact, 3 times as fast. Okay? So now let's, in another color, let's draw that function. We'll do it in black over here. First thing I would do is take the dislocation or the movement of the entire function in the y direction. I'm going to have 2, so I'm going to go up 1 and 2, and I'm going to draw a new axis. So the x-axis here has now moved up 2 units, and now all my movement is going to be about this dotted line, not the x-axis. Okay, that's moved everything up 2. Now this 3 tells me that the highest value is going to be 3 units above my new horizontal axis. So I'm going to go up 3 more units, 1, 2, 3, and I'll draw another dotted line there, and the function will not go above that. I will then come down 1, 2, 3 units, and I'll draw another dotted line, and I will say that the function will never go below that. Okay? So I've taken this into account, the amplitude. I've taken the vertical displacement 2 into account by moving the axis up, and now all I have to do is deal with this. Well, if one cycle of the normal sine is 2 pi, and I'm going 3 times as fast, then my new period is going to be the original period, 2 pi, divided by 3, because I'm going 3 times as fast. Okay, so that's 2 pi over 3. Now that's less than pi, okay? So we're going to start at the same spot. Let me put a different color for that. We're going to start at the same spot right here. Now we're going to go through a cycle in 2 pi over 3 radians. So let's say that this was pi and 2 pi. So if that's pi, then we're going to go at 2/3 pi. So let's just say it's right there. We're going to complete a cycle from here to here. Okay? So let's do that. We're going to divide that in half because we got to get back down to the axis. So we're going to go up, come down, all the way down to here, and come back up there. That will be its first cycle. Then we'll repeat that cycle and repeat it again. Okay? So we will do 3 cycles in 2 pi units. Okay? 2 pi radian units. So if this is 0 and this is 2 pi, we have accomplished 3 complete cycles in that, that space. So by looking at this, you can quickly say it's going to go up 2 units, it's going to spread out, +3, -3, about the new axis, and it's going to go 3 times as fast. So I can look at that And probably within about 15 seconds, I can see this, okay? And we went through it very slowly, but with practice, you can look at that, and that picture will come right into your brain, okay? So, that's just an example of what we would like to be able to accomplish. Be able to look at an expression and visualize the behavior of that. So I'm going to show this in some other example functions. So we're going to erase the board and come right back. Okay, welcome back. Now I use that trigonometric function to illustrate what we're trying to accomplish here, and that is taking the algebraic expression and creating a picture. So I'm going to look at some other functions that you're used to dealing with and do the same thing. So the first thing we're going to look at is a straight line, okay? So the simplest straight line is y equals x, okay? Now we can probably visualize that very quickly, okay? So y equals x, if you put in 0 here, then that means it goes through the origin. And for every one you go out, you go up, so we have a sort of stair-step type of activity going on here, out 1, out 2, up 2, and we can plot that as a straight line going right through there, okay? Now if I would change that to y equals 4x, okay, keeping this as sort of my frame of reference, 4x means I go out 1, go up 4, so what that would result in is a function that's much steeper, like that, okay? So this would be the y equals 4x going up much more rapidly. What if I had y equals 2x minus 3, okay? So what I can do there, using the black line here, I can say, okay, whatever I have in here, I'm going to move it down 3, okay? And if I plug in 0 for x, this is going to be 0. So when x equals 0, y equals minus 3. So I'm going to come down here and go minus 1, minus 2, minus 3. And that tells me that it's going to go through that point. Now I know that from that point, I go over 1 up 2. That's a slope. So over 1 up 2 would be about here. And then my new function would be going just like that, okay? So I think you can see that the formula you're used to seeing for straight lines, y equals mx plus b, is very easy to visualize if you will anchor it at the y-intercept and then envision what the slope would be. So I think we could do about anything we wanted with that. Now one other thing we could do, what if we wanted to move the intercept off of the y-axis? So let's look at this, for example. Let's say we have y equals 2 times x plus 3 plus 1. So we're going to put x plus 3 in a parenthesis instead of just x. 2 times x plus 3 plus 1. Okay, now how could we visualize that? Well, if you ask yourself what value of x will make this 0? If this is plus 3, then this x has to be minus 3, okay? Well, what that means is we're going to move the intercept from the y-axis over to a new y-axis, which is 3 units to the left. 1, 2, 3, okay? Now we can put in a new y-axis dotted to remind us it's not the real y-axis, it's just our reference y-axis. And it's going to go through here when this is equal to minus 3. This will be 0. It's going to go through at plus 1. So let's go up plus 1. So that's going to be where it passes my dotted y-axis. And it's going to have a slope of 2. So over 1, up 2. So over 1, up 2. And now we have the new line going just like that. Okay? All right, so that's how we can deal with the a straight line. What about a parabola? So I'll just go to the lower part of the board here. What if we have y equals x squared? Okay. Well, let's draw that. First thing we know is with this expression right here, there's no way y can be negative. Because when you square a number, it's always going to have a positive result. We also know that if x is 0, then y is 0. So we can take the origin. We know it's going to pass right through there. And then as you go over 1, you go up 1, you go over 2, you go up 4. As you go back 1, you go up 1. As you go back 2, you go up 4. And so we could lay in a parabola that looks like this. Okay? Now what happens if we change that and say y equals x squared minus 3? All that means is we're going to take this picture and move it down 3 units. And then we're going to draw a new parabola that will go right through here, has the same shape as this. Okay? And we would have that right there. Okay, what about if we want to offset it from the y-axis? So we could have y equals x minus 2 plus 1. This all squared. Okay? So how can we do that? Ask yourself, what value of x will make this equal to 0? The value of x, since this is minus 2, is going to be plus 2. So we're going to go over 2 units. Okay? And then when x equals 2, this is 0, so y equals 1. So we're going to go up. Like I said, we would put a dotted line here for a new axis. We'll go up 1 unit, and it's going to go through right there. And it would be the same shape as this. Same exact shape, but offset like that. Okay? So that's a parabola. You can do the same thing with a cubic. Let's just say y equals x cubed. Okay, let's think about that a second. When x equals 0, y equals 0, so we know that's going to go right through the origin. Now what happens when x gets big? When x is 1, you cube it, you get plus 1. When x is minus 1, you cube it, and you get minus 1. And then when you go to 2, you're going to cube that. 2 times 2 times 2 is 8. And when you go negative 2 times negative 2 is plus 2, times negative 2 is minus 8. So what we're going to have is a function that looks like this. And that's our standard cubic. And again, you could do everything to the cubic that you did to the parabola and you did to the straight line. Okay? Just moving it up, moving it down, moving it over, moving it back. Okay? Another one that you often see is the exponential. Y equals e to the x. Okay? Now, for years we have dealt with the line, the parabola, the cubic equation, where the variable is the base that we raise to some specified power. In this case, power of 1, power of 2, power of 3. With this, e is just a constant. It's 2.71828, and it goes on forever. Okay? And x is the actual variable that we're going to change. So if we want to plot that, which I'll do right here, well, what about when x equals 0? Well, let's see. If I have a number 2.718 whatever, and I raise it to the 0 power, by definition, that is 1. Anything raised to the 0 power is 1. So I know that that particular function is going to be anchored on the y-axis, when x equals 0, that puts it on the y-axis, at a value of positive 1. Now, when x goes negative, what do we do when we have a negative exponent? We flip it over, and it would be 1 over e to a positive x value, okay? So when I flip it over, and it starts getting big in x, meaning negative, we are going to get it smaller and smaller and smaller, and so this is going to come down to an asymptote. Will not cross the x-axis, but it'll get closer and closer to it. Now we're in the positive side. We don't have to flip anything over. We have a number, 2.71828, and we just start increasing that exponent. And when we put this to a decimal, then 1, 2, 3, 4, we find that this goes up very quickly. During this pandemic, we've talked about exponential growth. And this is what we're talking about. Things start low and then they get out of control. All right? Now we can move this around the same way. What if we had y equals e to the x plus 2? That would just say, well, instead of being here at 1, we're going to go up 2 units from there, and so it's just going to go through y equals 3, okay? We could also shift this from the y-axis and write it as y equals e to the x plus 2 plus 1, okay? What we would do there is say, okay, again, what value of x would make this equal to 0? Well, the value of x that would make that 0, since that's plus 2, is going to be minus 2. So instead of going through the y-axis at these reference points, I'm going to come back 2 units, draw a new y-axis, and then everything would be referenced to that, depending on what I wanted to do. Okay? So those are some of the traditional functions that you see, and when you face them, you can then see the picture. Now I'm going to return to the trigonometric functions and go through those in a little more detail. I'm going to erase the board, and then we'll deal with some trigonometric functions in a little more detail. Okay, welcome back. We're now going to revisit the trig function because it's the one we run into a great deal when we're talking about the various college level courses or some of your advanced classes in high school. All right, so first thing, let me say that I do not like to memorize things. What I've found in life is that if you memorize things and you don't use it a lot, it tends to fade. So what I've tried to do is have ways of figuring things out so that all I have to know is how to go about it and I don't have to remember the specifics. So let me show you what I mean by that. So let's suppose that we are trying to understand what the basic trig functions look like. Sine, cosine, tangent. All right? So when you use them all the time, you have it sort of memorized. Oh, this is that, and that's the other, and this does this other stuff. But when you don't use it a lot and you return to it, then you got to say, well, gee, did the sine start at 0 or did it start at 1? And does it have any places where it's undefined? Sometimes it's hard to remember all that. So here's how I do it. I draw a unit circle. Just a circle with it looks more like a pumpkin, but it is a circle. And then we just, in our mind, we draw a little triangle, okay? And I'm going to have the hypotenuse just be 1. Unit circle meaning the radius is 1, okay? And then this will be the opposite side, and this will be the adjacent side. Of course, that's the hypotenuse, which is 1. And this will be some angle. We'll use theta for the angle in this case. Now, every time this radius rotates around this circle once, we have gone through a period of motion because it increases its value, then it decreases value, then it goes negative, then it comes back here in terms of where it's going in this XY plane, okay? And as we do that, the trig functions are going to change because the trig function is, for example, sine is opposite over hypotenuse, and the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. Now, what I like to visualize when I'm at these axes is a sliver triangle. And what that would look like if I just drew the axes here, say the first quadrant, it would be a very narrow triangle. So the angle here, theta, approaches 0. Very small. Not quite on the axis, but very small. And then this would be my opposite side, this would be my adjacent side, and this would be my hypotenuse 1. Now that would also occur up here. So when I get near 90 degrees, I would be almost all the way up there. I would drop the perpendicular down like this, and this would be the angle going all the way almost to 90, and this would be my opposite side, this would be my hypotenuse, and this would be my adjacent side. Okay. Now if I can visualize those slivers, I can quickly remember what the value of the trig function is depending on how it's defined, opposite over hypotenuse or adjacent, or opposite over adjacent, or adjacent over hypotenuse or opposite over adjacent for the three trig functions. So let me show you how using the sliver concept and the unit circle going through a rotation can generate your various trig functions. So let's start with sine. So I'm looking for sine of theta, where this is theta. Okay? So I'm going to start right down next to the theta axis. In our way of thinking, this is the y-axis, this is the x-axis. We've changed that now to this being the y-axis, which is sine theta, and this being the x-axis, which is theta. Okay? So when I'm just starting, and I'm thinking sine is opposite over adjacent, I look at this little sliver, the opposite side is very, very tiny, and the hypotenuse is still 1. So a tiny, tiny number divided by 1 is a very tiny number. As I get all the way down to the x-axis, that collapses to 0. So that reminds me that the sine must go through the origin. Okay? Now let's rotate this up to where we're up at this place and ask ourselves what the sine is there. Well, the sine is almost the same length as the hypotenuse. Look at those two lengths. They're almost the same. So when I get out to pi over 2, which is 1/4 of the full rotation, I'm going to be up at a value of 1. So I'll put a little dot there. Now when I rotate beyond that, I start getting down here. The sliver reverses, okay? But I still have an opposite side of almost nothing compared to the hypotenuse of 1. So that brings me right down here at pi to the theta axis. Now as I rotate further, I'll get down to this location, 270 degrees, or 3 pi over 2. And again, I'll have this sliver upside down, okay? Well, when I'm upside down, the opposite side is now a negative value. The hypotenuse is still positive. So what happens then is at 3 pi over 2, I am down, just like this was plus 1, I'm now down at minus 1. And as I finish the rotation, it'll bring me right back to 360 degrees, or 2 pi, which gives me this sliver, but just reversed. Again, it's going to be at 0. Okay? So now, there's my trig function, just by visualizing how this rotates around there. Now let's do the same thing for cosine. Okay? We'll change color. We'll use black for that. So let's ask ourselves what happens with cosine. Well, when I start out, what's the adjacent side? the adjacent side is large. It's right out here, and it's basically the same size as the hypotenuse. So what that tells me is the cosine, all right, this is cosine of theta, it's going to start at 1, a value of 1. So it starts where that is at pi over 2 for the sine. Now it's going to go down as we rotate up. When we get up to 90 degrees, what's happened to the adjacent side? The adjacent side has disappeared. It's gotten very, very small. So that's going to put me down here. And we'll just continue that. And we'll end up right where we started. Now you might see something here. The cosine function looks very much like the sine function, except it's shifted. If you think about it, we've taken this and we've shifted it back here. We've shifted it back pi over 2 radians. And then from there on it goes. So there's a nice relationship between the sine and cosine function in terms of what we call a phase shift of either one of those along the theta axis. Okay? Now let's do the tangent. Okay? Again, unit circle. Let's ask yourself, what's the tangent when we start out at 0? So this is down here, the sliver is very small. This is 0. The adjacent side is basically the same size as the hypotenuse. 0 over 1 is going to be 0. So we know that the tangent function is going through the origin. Now let's ask ourselves, what happens when we rotate? Well, the opposite side gets bigger as we go up in value, and the adjacent side shrinks because we're coming toward the vertical axis. So what happens is we take an increasing number on the top and divide it by a decreasing number on the bottom, and when you take big on the top and little on the bottom, guess what? It gets real big fast. So what happens to this is this goes like this, and when we get to 90 degrees, what's happened to us? When we get to 90 degrees, we have taken the opposite side to be 1, but what's happened to the adjacent side? The adjacent side has shrunk all the way down to 0. Now we all know that if you divide anything by 0, you're going to get a very, 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 very large number. It's often called undefined or infinity. So what that means is, at pi over 2, this shoots off to infinity. Okay, it gets as large as any number could be. And so we often draw a dotted line right there, which basically says that can't cross that line. Going this way, you can't cross it. And that is called an asymptote. Okay, something that you don't cross, a limiting location. You just can't go past that line. Now what happens when you go past pi over 2? When you go over past pi over 2, this just reverses, okay? And now we have still a very large positive opposite side, but a very, very small negative value, okay? So what that means is it's going to start down here at negative infinity and then come up and cross the axis at when we get over here to pi, okay? So here's pi. Let's verify that. When you're over here, you have an opposite side that's very small, that's on the top, and an adjacent side has become 1. So 0 divided by 1 is 0. And so what happens here is this then starts replicating to another asymptote, and the same thing happens as we keep going. Come up, go through, and up like that. All right. So, by thinking of the unit circle and thinking of the rotation, we can very easily remember the sine starts at 0, goes through its cycle, the cosine starts at +1, goes through its cycle, and the tangent starts at 0, asymptotes at pi over 2, flips itself over and starts down at negative. If you think about that, the function is as big positive as it could be, positive infinity. And with the next little step, micro step, to cross that asymptote, you shoot down, like shooting through a wormhole in some of the Star Trek activities or concepts. You shoot through the wormhole, and instead of being at positive infinity, you are now at negative infinity, just like that. Now, how far apart are those two infinities? You can think about that all day long. How far apart is negative infinity from positive infinity? But that's how this function behaves. It goes to the asymptote, and just as it crosses it, it shoots itself down to negative infinity and starts the process all over again and cycles through. Okay, so with that background of the unit circle, we can easily deal with any of the sine, cosine, tangent functions. And we can also do it with the other three functions, the secant, cosecant, and cotangent. So I would invite you to think about what the plot would look like for the secant. Okay? So the secant of theta is equal to the reciprocal of the cosine. So it's 1 over the cosine of theta degrees. So let's think about that a second. Let's suppose I plotted and wanted to find out what the secant looks like. And I would say that's one that you don't know. Even if you've played with it, you play with it so seldomly that it's probably one you wouldn't know. Okay, so let's see how we would do this using our rotating right triangle through the unit circle. Well, when we're at 0, what is the value of cosine? Well, if we're at 0, we're down here, and the cosine is 1. Well, 1 over 1 is 1. So one thing I know is the secant crosses the y-axis at 1. All right? So we put a little dot there. Now let's ask ourselves, as we rotate through the first quadrant, what happens to the cosine? The cosine starts at 1 and starts decreasing, decreasing, decreasing. Look at it up here. Starts at 1, decreases, decreases, decreases until it gets to 0. Well, what is 1 divided by 0? Again, an undefined number or positive infinity. So we would draw an asymptote here at pi over 2, and this would go up like this there. So that'd be the first part of it. Now what happens when we get past 90 degrees? Well, what happens to the cosine? The cosine now becomes negative, okay, because we're now in the negative 2 quadrants for the horizontal axis, okay? And as you cross over here, what happens when you get clear to here? Well, the cosine becomes -1, okay? Because it's -1 here divided by the hypotenuse. So we're going to have -1 right down here. And this asymptote is going to go like this, and then it's going to continue like that to another asymptote. And we would just replicate that through hitting these barriers at each part of the cycle. Okay? So that's how you could do a secant. I invite you to do the same thing with the cosecant and also the cotangent on your own. Okay? So now we're going to finish with using this to do a complicated trigonometric function. So I'm going to erase the board and come back with that. Okay, welcome back. So now we're going to look at a trig expression and then use what we've learned so far to draw a plot of it. So let's look at y equals 2 cosine of 2x plus pi inside plus 3. Okay. 2 cosine, 2x plus pi inside plus 3. Okay. So first thing we notice is we have a cosine function. All right. Let's draw this. Here are our axes. Okay. So we know it's going to be a cosine function. We know what that means. It starts high, comes down, and returns. Starts at 1, comes down, and returns to 1. Okay? Now, let's get our boundaries. This says it's going to be whatever it is, you're going to add 3 to it. So what I'm going to do is take 1, 2, 3, and I'm going to draw my new horizontal axis at y equals plus 3. I know that this is going to determine how much, what the range of the values of the function will be for cosine. Instead of being from plus 1 to minus 1, it's going to be from plus 2 to minus 2. So we're going to come up 2 more units high and draw another set of another dotted line. We're going to come down 2 units, so it's from 3 to 2 to 1, and now I have that. Okay? So I've bracketed that, and you really wouldn't have to draw this when you're actually looking at it. You just say, all right, I know it's up, and I know it's spread. Okay? So you know it's up, and you know it's spread, and one thing you know is it's never going to go negative. Okay? Because the 3 puts you up high enough where you will never have a negative cosine function with all that expressed. Okay. Now, how do we handle this? Okay. So you take that, and in your head or on a piece of paper you can say, okay, 2x plus pi. Where does that equal 0? What value of x makes that equal 0? Okay. Well, let's say that equals 0. So let's take this to the other side. So 2x equals minus pi. Okay? And that's divided by 2. So x equals minus pi over 2. Okay? So that means it's going to center at minus pi over 2. So we'll come back here to minus pi over 2. And we'll say, guess what? That's going to start right there. It is shifted back minus pi over 2. Okay? Now, how fast is this going to go through its cycle? Well, the 2 says that it's going to go twice as fast as a normal cosine. So that means it's going to go twice as fast as 2 pi. Twice as fast means half the period. So it's going to go from minus pi over 2 over pi units. Well, if we go pi units, we're going to go over to plus pi over 2. So here's plus pi over 2. That would be a distance of pi, which is what that says it will be. 1/2 of 2 pi is pi. And so we're going to go through this cycle from here, and we're going to end it, the first cycle, right at that point. So here I go. I'm starting here with the cosine. The cosine starts up at the value of 2, okay? And then it's going to, and I want to end right up there. So I'm going to go down like this. And there I am. And then I would just continue that, every pi going through the same cycle. Okay? So, given that, which you look at, what the heck is that? I now have in my visual cortex, I now have this picture that it's starting at positive, in this case, 1, 2, 3, 4, 5. I'm starting at a value of 5. I'm starting to go through a cycle that occurs once every pi units, and I return to that 5 again and go all the way down to positive 1. So starts at 5, comes down to positive 1, returns to 5, comes down to positive 1, returns to pi, and all through there. So I think you can see the power of this. That's not an easy thing to visualize right off the top of your head, but with a little practice, you can look at that and say, I see that, I see this, I see what this is going to do, and I asked a simple question, what value of x makes this equal to 0? You can almost do that in your head. That tells you where you're going to start, and from there in you just layer in your expression. So I hope you've enjoyed this activity where we look at taking functions of different types and we quickly develop the skills for visualizing those functions. So when you face them, either in a textbook, on a problem set, or in a lecture, you can quickly say to yourself, I see the behavior of that function, and it's going to help me understand and predict what's going to go on as we move through the various oscillations for trig functions or growth in an exponential or straight line or parabolas or cubic functions. So I hope you enjoyed that. Practice it, and with practice you'll find you'll ingrain it and be able to use it the rest of your life. Thank you.